A spacecraft camera misses its shot as a new interstellar visitor, 3I Atlas, streaks past Mars. Then rumors spread that NASA is holding images said to be too sensitive to share. Officials say no aliens and no threat, yet a lone amateur captures Atlas at dawn while official silence prevails. As 9 mounting anomalies challenge comet science and ignite suspicion, are we witnessing a rare natural oddity or the relic of technology? Before Atlas vanishes, the evidence is piling up. On October 2nd and 3rd, 2025, 3I Atlas swept within 27 million kilometers of Mars, a rare opportunity for close-range imaging by the Mars Reconnaissance Orbiter HiRISE camera. HiRISE, known for delivering images at sub-meter resolution from Martian orbit, was reportedly tasked with capturing the object as it passed through the field of view. Yet as days turned into weeks, no high-resolution frames appeared on NASA's public data servers. Official statements remained absent, and the usual cadence of HiRISE releases slowed to a crawl. Rumors spread through scientific circles that the best images were being held back, either for calibration, technical review, or as a result of administrative delays tied to a recent US government shutdown. The standard HiRISE workflow involves raw and calibrated frames, engineering logs, and detailed pointing metadata, all typically available within weeks of acquisition. For the Atlas Pass, requests for these products, EDR and RDR images, observation logs, and SPICE kernels, met with silence. The RAID 4 CCD failure, which had reduced the camera's field of view months earlier, complicated the picture further. Still, the expectation remained that at least partial frames or engineering data would be released for independent analysis. Instead, the absence of even basic metadata or status updates left a vacuum. As the days ticked by, calls for transparency grew louder. Lawmakers and scientists issued formal requests for HiRISE data, citing the urgent need for independent verification before Atlas left the inner solar system. The lack of clarity over the data's status, whether under technical review, embargoed, or simply delayed, fueled suspicion and frustration. For a fleeting interstellar visitor, every lost day narrows the window for discovery, and every missing dataset raises the stakes for open science. In the early hours of November 2nd, 2025, a single observer at the LOL Observatory set out to catch 3I Atlas just above the horizon. The telescope, a modest 152mm Ritchie-Chrétien, was never designed for deep sky imaging under such difficult conditions. Dense humidity clung to the air, and dawn light pressed against the faintest signals. Still, the observer pressed on, adapting with makeshift dew shields and a custom guiding script to keep the target centered. Over a series of short exposures, the faint track of Atlas appeared where predictive ephemeris said it would, a testament to both preparation and perseverance. What makes this image stand out is not just the technical challenge. It is the fact that, while institutional data remained locked away, an individual with a small scope and a willingness to collaborate online managed to capture a verifiable record. The observer logged every detail: timing, coordinates, weather, even the quirks of local seeing, then posted the raw data to community forums for peer review. Within hours, amateur networks had confirmed the detection, stacking exposures and matching the object's motion frame by frame. No embargo, no delay, just open data available for anyone to scrutinize. This episode highlights the unique power of citizen science. When official channels stall or go silent, distributed efforts can still deliver. Each independent observation, no matter how humble, adds a layer of accountability and resilience to the larger search. The LOL Observatory image became a rallying point, not just for what it showed, but for how it was shared, openly, transparently, and with an eye toward collective verification. A single tweet can travel faster than a formal report. In the case of 3I Atlas, NASA's public relations team moved quickly to reassure the world with the message, "No aliens." That line, delivered with the finality of a stamp, became the viral soundbite. It ricocheted across social media and news headlines, shaping first impressions before most scientists had even reviewed the raw data. Meanwhile, formal requests from researchers and lawmakers for technical details, especially regarding the missing high-rise images stalled in bureaucratic bottlenecks. Days stretched into weeks with no substantive response. Congressional letters went unanswered. International science bodies waited for clarification on the observation logs and image status. The contrast was hard to ignore: a rapid, blanket dismissal in public, but silence or vague assurances in official channels. This mismatch between public messaging and technical transparency has become a familiar pattern in high-profile discoveries. The absence of detailed, timely responses to the scientific community creates a vacuum that speculation quickly fills. Rumors about withheld images, unexplained delays, and internal reviews gain traction when the facts are slow to surface. Scientists warn that credibility hinges not on reassurance, but on open, reproducible evidence. As the window for independent observation narrows, the need for clear, consistent communication grows more urgent. The credibility of any finding, natural or engineered, rests on the willingness to share data and address legitimate questions, not just to manage headlines. In the story of 3I Atlas, the gap between institutional messaging and technical disclosure has become part of the mystery itself. Laboratory results from several research teams have sparked new controversy over the composition of 3I Atlas. Early public statements describe the object as iron-nickel rich, a familiar profile for certain asteroids and cometary nuclei. But as spectra from ground-based and space telescopes were analyzed, a different pattern surfaced. Nickel appears to dominate, with iron present only in trace amounts. Some labs report nickel to iron ratios far exceeding those found in solar system bodies, and water content is estimated at around 4% by mass. This unusual metal signature has raised pointed questions among planetary scientists. In natural objects, iron and nickel usually track together, the product of slow condensation in stellar nurseries. Nickel-heavy material, especially at these levels, is rarely observed outside of processed meteorites or remnants of differentiated bodies. The debate has grown sharper as teams at Carnegie and Caltech publish conflicting reductions, each defending their calibration methods and error bars. Avi Loeb, a leading astrophysicist, commented, "If confirmed, this composition hints at non-solar system origin or post-formation modification." The stakes now rest on the release of raw, high-resolution spectra, so that independent researchers can scrutinize the data and resolve whether Atlas's metallic fingerprint is a quirk of nature or a clue to something more engineered. ALMA's radio tracking has delivered a puzzle that won't go away. The object's path shows a steady, measurable acceleration, one that cannot be explained by gravity alone. For a comet, the usual culprit is outgassing. Our jets of vapor and dust, kicked off by sunlight, push the nucleus and nudge its orbit. But the numbers do not add up. Calculations show that to match the observed acceleration, 3I Atlas would need to lose 15 to 16% of its mass over the observed period. That kind of mass loss should produce a sprawling, bright coma, a cloud of debris and gas visible in both optical and infrared. Instead, telescopes find little more than a faint, compact envelope. No major jets, no thick dust plumes, no telltale signs of violent activity. Solar radiation pressure falls far short of the required force, and no known natural mechanism fits. Some researchers have floated more exotic ideas, from unseen fragmentation to non-standard physics. As the next observation window approaches, the focus sharpens. High-resolution imaging and spectroscopy must hunt for subtle jets, hidden debris, or any fresh clue that can resolve this momentum paradox. The coming months offer a rare, decisive window to test 3I Atlas against every known yardstick. Between late November and January, as Earth draws within striking distance, closest on December 19, 2025, astronomers will deploy the full arsenal: spectroscopy to probe for unusual gases and processed metals, polarimetry to track the extreme negative polarization, radio tracking to refine acceleration models, and deep imaging to hunt for jets or hidden debris. These efforts are shaped by 7 anomalies that set Atlas apart. Its orbit is retrograde, yet it hugs the ecliptic within just a few degrees, a configuration seen in less than 1 out of 300 interstellar paths. The dust tail sometimes points sunward, defying standard comet physics. Mass and speed combine at levels unmatched by any solar system object of similar size. 3 planetary encounters, Mars, Venus, and Jupiter, unfold within weeks, each coinciding with major conjunctions. Optical polarization plunges to record negative values, while the inbound trajectory passes within 2 degrees of the legendary WOW signal coordinates. At perihelion, Atlas brightened sharply and shifted to a bluer hue than the Sun itself. Each anomaly demands independent verification. Only through open, coordinated observation can the true nature of this interstellar visitor be revealed. On October 2, 2025, 3I Atlas passed within 27 million kilometers of Mars. That close approach was reportedly captured by NASA HiRISE, yet those images remain unreleased. In contrast, a single 152mm telescope at LOL Observatory secured public ground-based images just weeks later. Across the investigation, 9 distinct anomalies have been documented. A retrograde orbit near the ecliptic, a sunward anti-tail, very large mass together with very high speed, precision planetary encounters, an unusual nickel-to-iron ratio, extreme negative polarization, a trajectory near the WOW signal region first noted in 1977, perihelion brightening with a bluer than sun color, and a mass loss paradox without visible debris. Despite extensive scrutiny, the true cause of 3I Atlas's non-gravitational acceleration remains unresolved. Key data on composition and dynamics are still held by multiple institutions. With Earth's closest approach set for December 19, 2025, the need for open data and independent verification is clear. Whether 3I Atlas is a rare natural fragment or the product of unknown engineering, the evidence demands full transparency. Because only facts, not speculation, can answer what this object truly is.